Hello, in this video we're going to go over the organization of the periodic table. Now, the periodic table is one of the cornerstones of chemistry because it organizes all of the elements on the basis of their chemical properties. So what we're going to find is that all of the columns in the periodic table contain elements that have similar chemical properties. But we'll also notice some other trends in the periodic table as well. Now, one thing I did want to mention, down below, you'll notice these two rows that are separate from the periodic table. So those actually do follow the rows in the periodic table, but if we placed those two rows into the periodic table, it would be super wide. So we would actually see a gap right here, and it would be hard to fit the periodic table on a piece of paper or even onto this slide. So we tend to separate out those two rows. But we're not going to deal with those elements this quarter, so don't worry about them. I just wanted to show you that those two rows actually do exist in row 6 and 7, but they're just really long, so we tend to move them out of the periodic table. All right, so let's talk about metals, nonmetals, and metalloids. So every element can be classified as either a metal, a nonmetal, or a semi-metal, which we sometimes call a metalloid. And we're pretty familiar with metals, right? They're typically shiny, they're typically silver in color, other than things like copper, which is usually kind of a bronze color. And metals are also excellent conductors of electricity and heat. They're also malleable, which means that they can be shaped into sheets. And they're also ductile, which means that they can be drawn into wires. So you might notice that there are copper wires and copper cookware. So a lot of metals can be shaped for our needs. And you'll also notice down below, the majority of the elements on the periodic table are classified as metals. So that entire left-hand side of the periodic table and the middle, those are all metals. One exception you'll notice is hydrogen. Hydrogen is a non-metal because remember, hydrogen is a gas. So it doesn't follow the typical indicators of a metal, right? But we do list it in column 1 on the periodic table because each of the elements in that first column have one valence electron. So they all have similar chemical properties. And we'll get more into that later. Now, nonmetals are typically dull. They're usually poor conductors of electricity and heat, and solid nonmetals are also very brittle. So for example, pencil lead is actually not lead, it's carbon, and carbon, when it's a solid, is called graphite. Or a diamond, I guess. Diamonds are also made of carbon. But graphite is very brittle, right? And we can't conduct electricity or heat using your pencil graphite. So that's one example of a nonmetal. A lot of the nonmetals are actually gases. So for example, in the last column, we have helium, which is a gas, neon is a gas, argon is a gas. We also have nitrogen gas, oxygen gas, but we do have some solids. So for example, sulfur, which is right below oxygen, is a yellow solid, and it's very brittle. and kind of dull. It's not shiny like a metal, right? Okay, so we're hopefully pretty familiar with a lot of nonmetals. Now, you'll notice that the semi-metals are in between the metals and the nonmetals. So the semi-metals are boron, silicon, and silicon is actually what's used in computer chips. So that's why in California, where all of the big tech companies are, they call it Silicon Valley, because silicon is typically used in computer chips. Although they have found other things that they can use in computer chips as well. Below silicon is germanium, and then we have arsenic next to that, which is poisonous. It's toxic, right? Below that, we have antimony, which has the symbol SB. Next to that is tellurium, and underneath that is polonium. So those are the semi-metals. You don't have to have those memorized, but just in general, know where the semi-metals exist on the periodic table, right? So we have this zigzag line to kind of help us visualize where the semi-metals are. Now, you might be tempted to list aluminum as a semi-metal, but aluminum is a pure metal, right? We use it in soda cans, for example. So that's definitely a metal. It's shiny, it can conduct heat and electricity. So that is not a semi-metal. Now there is another way to categorize the elements, and that's by naming certain rows or certain columns of the periodic table. Now you'll notice here we have the first 2 columns and the last 6 columns categorized as the main group elements. The other name for these elements are the representative elements. Now, these are the elements that we're going to deal with the most in our class. So, for example, in the middle, we have the transition metals. And we're not really going to deal with transition metals too much in this class, so you don't have to worry about those as much. And I also mentioned that the 2 rows below the periodic table we're not going to cover, but those are called the lanthanide metals and the actinide metals. So we're really going to deal with those main group elements, and you'll notice that the first 2 columns have specific names, and the last 2 columns have specific names. So let's go over those. But first, let's talk more about the number of rows and the number of columns. So the rows of the periodic table are also called periods. And periods have different lengths. So the first period or row has only 2 elements, hydrogen and helium. And then the second and third periods, so rows 2 and 3, have 8 elements. And then below that, we have the fourth and fifth periods, and they have 18 elements each. And then later periods, again, are really, really long. So we separate out some of those elements so that the periodic table is more compact. Now, the columns in the periodic table are generally called groups or families. Earlier, I mentioned that the columns of the periodic table contain elements that have similar chemical properties. So that's why we call them families. But again, typically we call them groups as well. Now, we mentioned the first 2 columns have specific names. The first column of elements are the alkali metals, and the second column is called the alkaline earth metals. The very last or actually the second to last column, those are called the halogens. And then the very last column, that is referred to as the noble gases. So down below we can see sodium and lithium. So sodium and lithium are both metals, and they're both in column 1 of the periodic table. So they are called alkali metals. So sodium and lithium are both shiny until they're exposed to air. So you'll notice that where these were cut, they don't look very shiny anymore. And again, that's because they were exposed to air, so they're oxidizing. But they do have very similar chemical properties to each other. So again, the alkali metals in group 1 are lithium, sodium, potassium, rubidium, cesium, and francium. Remember, hydrogen is not an alkali metal. It's actually a gas, but it's included in column 1 because it has the same number of valence electrons as the other elements in column 1 or group 1. Now, sodium is a pretty common element. It's present in table salt, which is also called sodium chloride. Lithium is also pretty common. It's found in batteries, so lithium batteries, right? And it's also used as a pharmaceutical drug. Now, you have to be careful with alkaline metals in general because they are very reactive with water. So if you go to YouTube and you look up sodium and water reaction, you're going to find videos where somebody puts a piece of sodium or maybe lithium or potassium in some water, and it starts to fizz and spark, and sometimes it even causes an explosion if there's enough of it. And part of that has to do with the fact that these metals only have one valence electron, and they really want to give up that electron, and we'll talk about why later. Now, the alkaline earth metals are in group 2, so that contains beryllium, magnesium, calcium, strontium, barium, and radium. Up above, I have a picture of magnesium, and you can see this is clearly a metal as well. It's very shiny, it's silvery in color, so very typical of a metal. Now, beryllium, strontium, and barium are pretty rare, and radium at the very bottom is very unstable and highly radioactive. So we don't really deal with that. Now, calcium and magnesium, on the other hand, are the 5th and 6th most abundant elements on Earth. And you might have heard of magnesium supplements. Those have become very popular recently. They're said to help with things like sleep. And then calcium is really important for bone development, teeth development. So those are very, very abundant elements. Now, the alkaline earth metals are not as reactive as the alkali metals, so that's a good thing, right? Because if we're taking these supplements, we don't want to have them react with us because we're made mostly of water. Now, the second to last column we refer to as the halogens. So this includes fluorine, chlorine, bromine, iodine, and astatine. At the very bottom is tennessine, but we don't really work with that at all. So the main ones we're going to work with or talk about are fluorine through iodine. Now up above you can see some pictures of chlorine, bromine, and iodine. So chlorine is a yellowish green gas. Remember, it gets its name from the Greek word chloros, which means yellow-green. Bromine is actually a liquid, and iodine is a purple solid. So that's kind of interesting. As we go from chlorine down to iodine, we have a gas, then a liquid, and then a solid. Now, even though they have different physical states at room temperature, they do exhibit very similar chemical properties, which is why they're all in the same column or group. Now, compounds that contain the fluoride ion are added to toothpaste and water to prevent dental cavities. Fluorine's also found in that non-stick coating on kitchen utensils called Teflon. Bromine and iodine are less abundant than chlorine. Chlorine we've used in a lot of things. So chlorine can be found in table salt. It's used to help clean pools. So chlorine's a little more abundant. Now, astatine is radioactive, so it exists in very negligible amounts, and tennessine is the same. So we don't really talk about those too much. Now, finally, we have our last group, group 8, the noble gases. Now, the noble gases are helium, neon, krypton. Oh, I skipped argon. Argon, krypton, xenon, and radon. Now, the noble gases are actually really, really stable on their own. So they exist as single atoms. Now, remember, previously we talked about how some atoms are unstable on their own. So they form diatomic molecules like hydrogen, nitrogen, oxygen, etc. But the noble gases are very stable just on their own. So at room temperature and pressure, they are unreactive. They don't really like to react with anything else. In order to have them react with something else, you have to provide a lot of energy. Now, because of their low reactivity, they can be used, for example, in lights, like neon lights. They can also be used, argon is used as or is used for welding and in light bulbs, etc. So they, again, are very, very stable elements. Now, one thing you might have noticed as we've gone through the columns or the groups is that the last two I called group 7 and group 8, but they're listed as 17 and 18. So, if we look at the entire periodic table from left to right, there are 18 columns. However, if we're just looking at the representative elements, so let's go back. If we're just looking at the representative elements, we can number them 1, 2, 3, 4, 5, 6, 7, and 8. So that's why there's two different sets of numbering schemes. It depends on if you're looking at the entire periodic table or just those representative elements. So either numbering scheme is correct. All right, so let's go back. So now that we've talked about the noble gases in the last column of the periodic table, we can talk about noble gas configurations. So noble gas configurations can be used to abbreviate really long electron configurations. So this is going back to our last video where we talked about electron configurations. So why can we do that? Well, it has to do with the fact that noble gas electrons completely fill each energy shell. So, for example, neon, which is element number 10 on the periodic table, has 10 electrons, right? So neon has 10 electrons. Now, if we fill up our electron hotel with those 10 electrons. I'll just write that real quick. Remember, the first 2 electrons are going to go in the lowest energy shell, which is the 1s shell. The next 2 electrons will go into the 2s shell. And then remember, the 2p shell, which is the next highest energy shell, can hold a maximum of 6 electrons. So that gives us 10 total electrons, and we've completely filled in row 1 and row 2 of our electron hotel. So shell 1 and shell 2. So the electron configuration for neon is 1s2, 2s2, 2p6. Now, if we go to the next element, which is sodium, so sodium is number 11 on the periodic table. So it has 11 electrons. We're still going to fill in shell 1 and shell 2, right? So the beginning of its electron configuration is 1s2, 2s2, 2p6. But that 11th electron has to go somewhere, right? So for sodium, we're going to put that extra electron, the 11th electron, in the 3s subshell, because that's the next highest shell, or subshell. So 3s1. So what we can do to abbreviate this is we can replace the first part of that electron configuration for sodium with neon in brackets, because neon's electron configuration is 1s2, 2s2, 2p6. So the abbreviated electron configuration would be neon in brackets followed by 3s1. Now, the other really handy thing about noble gas configurations is you can see what the valence electrons are for an element. So for sodium, we just have 1 valence electron because remember, valence electrons are the highest energy electrons, so they're going to be in the highest shell. So for sodium, that is level 3 or shell 3, and there's only 1 electron in that shell, so that is sodium's 1 valence electron. So let's practice this a little bit more. So try to figure out what is the electron configuration of helium, which is a noble gas. And try to write the abbreviated or noble gas configuration for lithium, which comes right after helium. So I'll let you work on that. Pause the video, and when you're done, we'll go over it together. Okay, so how many electrons does helium have? Well, its atomic number is 2. So that means it has 2 protons, and if it's electrically neutral, it has 2 electrons. So the electron configuration would just be 1s2. So it only has 2 electrons, so those will both go in the lowest energy shell, the 1s shell. Now let's write the electron configuration for lithium. So how many electrons does lithium have? Well, lithium has an atomic number of 3, so that means lithium has 3 electrons. So its electron configuration, its full configuration, would be 1s2, 2s1. And we saw that before when we were talking about electron configurations. Lithium was our main example. But notice that helium has an electron configuration of 1s2. So we could replace the 1s2 in lithium's configuration with helium in brackets. And lithium has one valence electron, which is in the 2s subshell, and that is also shown with the abbreviated electron configuration. All right, so now let's do the same thing for magnesium. Let's write an abbreviated configuration for magnesium. Now, what noble gas comes before magnesium? Because that's the noble gas we're going to use to abbreviate the electron configuration. So I'll give you a second to figure that out. So feel free to pause the video and then we'll go over it together. Okay, so magnesium, how many electrons does magnesium have? 12, right? The atomic number for magnesium is 12. So let's start filling in our electron hotel. So we'll start with 1s2, then 2s2, then 2p6. Okay, so that is 10 electrons, right? 2 plus 2 plus 6. And we have 2 electrons left. So those can go into the 3s subshell. Now, the noble gas that comes before magnesium is actually neon. And remember, neon's electron configuration is 1s2, 2s2, 2p6. So we can rewrite this as neon in brackets followed by 3s2. So this tells us that magnesium has 2 valence electrons. So again, let's just go back to a periodic table. So we'll just kind of zoom in on this one here, because I just want to show you when we do those noble gas configurations. So magnesium is right here, and sodium is next to it. So if we want to write the abbreviated configuration for sodium or magnesium, we have to look at the noble gas that's in the row right before it. So that's going to be, let's see, we'll go up to row 2 and over to the end, and we get neon. So let's say, just for example, that we wanted to write the abbreviated configuration for strontium down here in row 5. So we would go up one row to row 4 and all the way over to the end, and that would give us krypton. So krypton would be the abbreviation we'd use in the first part of strontium's electron configuration, if that makes sense. All right. So I just kind of wanted to visually show you what's going on there, but let's go back and talk a little bit about the connection between valence electrons and the group number. So earlier I told you that if we're just looking at the representative elements, we can number them 1 through 8, or the columns 1 through 8. What's really handy about that is those numbers also correlate with the number of valence electrons. So everything in row 1 has column 1, I'm getting my rows and columns mixed up. Everything in column 1 or group 1 has 1 valence electron. Everything in group 2 has 2 valence electrons. Everything in group 3 has 3 valence electrons, so on and so forth until we get to the last column, which all of the elements, the noble gases in column 8, have 8 valence electrons. So that is a really handy way to remember how many valence electrons something has. The reason we care about valence electrons, again, is because this is going to determine how atoms interact with each other. Do they transfer electrons? Do they share electrons? So we'll get into that later on. Okay, so let's practice. Let's identify the number of valence electrons for the following elements. So see if you can figure out the number of valence electrons on your own for each of these elements. So pause the video, and when you're done, we'll go over it together. All right, let's look at neon. So which group is neon in? Group 8. It's one of the noble gases, right? So that means it has 8 valence electrons, which again, I'm just abbreviating as VE. What about boron? Which group is boron in? Group 3. So that means it has 3 valence electrons. And silicon? And remember, silicon has the symbol Si. So it's not sulfur. Sulfur has the symbol S. So Si, this is in group 4. So this has 4 valence electrons. Now sodium, we already said, was in group 1 and has 1 valence electron. Oh, my 1 looks like a 7 there. It's group 1, 1 valence electron. What about chlorine? Which group is chlorine in? Group 7. So this is one of the halogens. So this has 7 valence electrons. And what about bromine? So bromine is also a halogen. It's in group 7. So it also has 7 valence electrons. So again, chlorine and bromine, because they're in the same group and have the same number of valence electrons, they exhibit very similar properties to each other. All right, so one last thing we're just going to cover here in terms of periodic trends. We're going to look at the size of these atoms or elements. So let's talk about atomic radius. Now, you might remember from your math classes that if you have a circle has a diameter, which is the full width, right? And the radius is half of that. So that's what we're considering when we talk about atomic radius. So the periodic table is also useful for understanding atomic radius and kind of keeping track of the relative size of atoms. So as we go down a column on the periodic table, the atomic radius increases. And that's just due to the fact that we're increasing the number of electrons, and we're going to higher energy shells when we're increasing those electrons. So for example, lithium has 3 electrons. And remember, its valence electron was in the energy level 2, or N equals 2. And then sodium has 11 electrons, and remember its valence electron was in energy level 3. And then we could keep going, right? So potassium has 19 electrons, and its valence electron will be in energy level 4. So that's why the size of the atom increases as we go down a group or column. Also, I had mentioned previously that the higher the shell number, the farther from the nucleus the electrons in that shell are likely to be. And now we know why. they're going into higher energy shells, right? Now, what if we go across the periodic table? So we go across a row or period. Um, we're actually going to see the atomic radius decrease. So for example, let's look at lithium versus neon. The numbers underneath are the atomic radius. So lithium has an atomic radius of 152, and I believe the unit is in something called angstroms. Neon has a radius of 70, so it's much, much smaller. Now that doesn't quite make sense with what we just said, right? Because we know electrons are increasing as we go from left to right. Lithium has 3 electrons, neon has 10. So why is the atom getting smaller? Well, even though we're adding electrons, the electrons are being added to the same valence shell. So remember, lithium has valence electrons in energy level 2. Sodium's valence electrons are also in energy level 2. Now, the more electrons we add to that shell, so let's say we have 2 shells, right? They're going to be attracted to the positive charges in the middle of the atom, in the nucleus. So those protons, right? So the increased amount of positive charges in the middle, because remember, lithium has 3 protons, but neon has 10 protons. So neon has much more positive charge, all localized in the center of the atom. So those 10 electrons are going to be more attracted to the nucleus. So they're going to shrink in a bit. Whereas with lithium, we only have 3 protons, so only 3 positive charges. So its 3 electrons are not going to be that attracted to the nucleus, so they might spread out a little bit more. So that's why lithium is a little bit bigger than neon, because lithium does not have as many protons in the center. So remember, when we're going down a column, we think about the number of electrons. So the more electrons an atom has, the bigger the atom. But when we're going across a row, the size is going to decrease going from left to right because we're adding more protons, more positive charges. Okay, so let's practice. So question 1, which atom is bigger? An atom of lithium or an atom of fluorine? And then question 2, which atom is bigger? An atom of sodium or an atom of rubidium? So remember, double check if they're in the same row or in the same column, because that's going to help you decide which one is bigger. So I'll let you pause the video, and when you're done, we'll go over it together. All right, let's compare lithium and fluorine. So are they in the same row or the same column? The same row or period, right? So lithium and fluorine are in the same row, which is also called a period. So that means we want to look at the number of protons, right? So lithium has 3 protons. Fluorine has how many? Let's see, let's go back. So fluorine is number 9 on the periodic table. So it has 9 protons. Its atomic number is 9. I almost looked at its valence electrons, but we're thinking about protons, right? So since fluorine has more positive charges in the middle, that means its electrons are going to be very attracted to the nucleus. So they're going to shrink in a little bit. So lithium is bigger than fluorine. So remember, when you're going across a row of the periodic table, it's almost the opposite of what you would expect, right? Now let's look at the next question. Let's compare sodium and rubidium. So are they in the same row or the same column? The same column, right? So sodium and rubidium are in the same column, which we also call a group. So now we can think about the number of electrons. Now, rubidium is further down the column. So sodium is here, rubidium's down here. So rubidium is going to be bigger because it has more electrons. Okay, so that's it for chapter 2. I do want to reassure you when I ask you something about atomic radius on a quiz or exam, for example, I'm not going to ask you to compare, let's say, the size of oxygen to strontium, right? I'm always going to give you two atoms that are in the same row or two atoms that are in the same column. So I'm not going to trick you with something like that. Don't worry about that. Now, in the next chapter, we're going to start getting into those valence electrons and whether they're transferred or shared between atoms. So we'll start talking about chemical bonding. So I will see you then.